Good morning to the 4 of you that are here and the bunch of you that are online right now. We'll wait. It looks like the recording is still starting, so I'll wait for a second until that boots up. All right, there we go. So good morning. Welcome to second to last week of Thermo. And this is because Thermo is a little bit of a funky class and that we meet only once a week. This is not to say next week is not important, but this is the last class where we're going to be covering final exam type material. Next week, really what we're going to do is 2 different things. We're going to have review for the final, and we're going to go through and try to dig a little bit deeper into more physically what things like entropy and internal energy, what they actually are, which I think is interesting to get a little bit better, get your mind around what these things are a little bit better, although that's not going to be something specifically on the final. But we will have exam review stuff that obviously will be nice. So that's what's happening next week. But the cool thing is this is like the last final exam type content. Yeah, obviously, there's also an election happening today. So hopefully you have a chance sometime in your day today. Maybe it's right after this class because we were scheduled for 2 hours, but have a chance to go and vote in the election. Take time to do that. I know this is the time of the semester where we feel like we don't have 10 minutes to spare, much less, an hour and a half, but it's worth, take the time, take the effort, even if, in aggregate, your vote doesn't matter that much. It does matter. It's, it's something that's going to be important to do. So hopefully you get a chance to do that and carve out some time today for that if you haven't already. What's happening today in Thermo? So I just wanted to pull up, I haven't done this in a while yet, or a while now, but I wanted to pull this up just to talk over a couple things that are happening today and just make note of some things. The big thing that's happening today in Thermo is quiz number 5. Quiz number 5 is ostensibly due today at 11:59 p.m. You have 30 minutes to do the quiz. One thing that's a little bit different, so this quiz is open notes. I'm expecting it to be open notes. So spend a little bit of time beforehand getting things out and ready so that you know where they are and stuff, so that you're not saying, oh, I should really have, my notes from the last week or something like that. So spend a little bit of time, get your homework out, get your notes out so that you have that stuff in front of you. The other thing to know, have your compressibility chart handy. So there will be something where you might need that. So have that out and handy as you're kind of getting stuff ready, getting prepared to take the quiz. The other thing to note because this is a little bit longer of a quiz, it's a 30-minute quiz, 30 points. I want to make sure that you have ample opportunity. Those are words, right? You have ample opportunity to get partial credit for the work that you did partially correct. So when you're done taking the quiz, scan, take a picture, however you want, and just email me that document so that I can look it over and give you partial credit. If there's a huge delay or going to be a huge delay for whatever reason between when you're finished taking the quiz and when you're going to send me an email, just let me know. I mean, that's not a big deal. If I drop my phone in the toilet and now my phone doesn't work and I have to find somewhere else to scan it, just let me know. But if it's 3 days later and you never contacted me and you're like, oh, by the way, here's my work. And all of a sudden I'm like, where did this come from? I haven't seen this before. So just let me know, keep me in the loop. More than willing to work with you on whatever's going on, but just let me know. The other thing I just have as a note there, you may find it useful to go through this week's participation assignment prior to taking the quiz. It's not required, it's not exactly like the quiz, but you might find it useful to go through as just kind of another check of some somewhat similar material to what's on quiz 5. Especially there are 2 questions in the participation assignment. One of them is maybe more relevant than the other, but it's relatively short to go through, so that might be a good thing to go through before you trying to take the quiz. Then again, that's out of the way for you later. The other, what else to note? I guess the last thing to note, so it is election day. The quiz is due at 11:59 today. If for some reason you're like, can I just do it tomorrow? I can work with you. If there's some circumstance that you want to take it a different day, like tomorrow or Thursday, I can work with you, right? It's supposedly due today. If you can, that's great. If there's some reason that it should be adjusted, let me know and we can work with that. So that's everything about the quiz. 30 minutes, 30 points. This is our last quiz, which is good. This is also kind of the last check for yourself. I mean, think about it this way. This is the last check for yourself. Like, how do I know some of the, right? I feel like we know pretty well, and you've shown that you know pretty well how to do energy balances and how to apply the second law and how to do some of these things. What we're doing is shifting these and now doing them kind of in a more theoretical way, a more theoretical framework, which means that there are a lot more equations to memorize and figure out, like, when does this apply and when does it not apply and how do I use all these different ones. So this is a good check, like, how am I on that front? How am I working with the different equations that I have and figuring out different situations where they apply and where they don't. Okay. The other stuff going on, homework number 10 is a little bit longer than most of our homework assignments. It's a 25-point assignment, not a 20-point. So just budget that into your time over the next week. This will be our last homework assignment. So we don't have anything going on next week before exams. So this will be kind of our last push before exams for this class. But because of that, it's a little bit longer. It's a little bit longer than I maybe would have liked, but it's not crazy. So I don't think you'll find it like it's crazy long. I just want to let you know it's a little bit longer than some of our previous assignments. So because of that, because we have a quiz, because we have a little bit longer homework assignment, there is not a required lecture video. The lecture video that there is, it's about I don't remember how long it is, like a 12-minute, something like that. It's an example problem, so you might find it useful. It's not required. If you don't want to listen to me talk about the example problem, you can go down here and you can just pull up the notes that I go through. And one of the things that I'll just note about this example problem now, this is the exact same problem that we solved on, I think it was homework number 8. I don't know, I have it written there. It's like homework 8, question 3, the first time we solved a Brayton cycle. This is the exact same problem. We're just solving it now. Instead of looking up numbers in Cat 3 and doing that kind of a method, we're solving it now using some of these equations and principles that we're starting to deal with. So hopefully you see some of the connection between how we did it before, how we're doing it now, why they're different, how they're the same. The process is the same. We're still doing energy balances around the circle. We're still using things like, we know the process is a delta S equals 0 process, so that tells us something about how we get from one side of the turbine to the other side, things like that. So there's a lot of connection. But I'm doing the exact same problem intentionally so that hopefully you can look at some of those side by side and see where they connect, see how the stuff that you've learned before connects to the stuff that we're doing now. So I think it's a useful example problem. It's not required that you watch the video. It might be enough to just pull up the solution and print that out and kind of look at it alongside the previous solution, but the video is there. It's not, I try to go through it relatively quickly. It's not super long, so it may be worth watching. So that's kind of the general goings on in thermo. So I guess let's let's dive in today. And we're going to start by just kind of a brief recap. I'll keep it really brief of what we've done. And I'll say next week we're going to do I will do a better job, like trying to recap and put together what would be like beginnings of your final exam note sheet. Like, how do we keep all these different things straight, and where do they go, and how do they apply? We'll work through some of that next week. But today, there are a couple pieces of like important review material. So the first key point, delta U, delta H, and delta S are all path independent. So when we're doing some of these calculations, we're doing them along a specific path, but that's okay because they're path independent. So as long as we have a starting point and an ending point that's the same, it doesn't matter how we get between those two. We can do it in a reversible path, or whatever path makes our calculations the easiest. The equations that we've come up with, we have delta U, the integral from T1 to T2 of CV dt, right? The constant volume heat capacity, that goes with delta U. We have the constant pressure heat capacity, which goes with delta H. And then we had, right, for an ideal gas, we could relate the two heat capacities by R, the gas constant. And for an ideal liquid or solid, right, that means incompressible. For an incompressible liquid or solid, then the two heat capacities are the same. The one that's a little bit goofier is entropy. So, right, we had in the videos from last week, we could do an energy balance. Along a reversible path to get two different equations. We had T ds was du plus P dV, and TdS equals dH minus PdV. So those two equations are kind of linked together. They're kind of weird equations. We've gone from, like, we jumped a little ways into calculus to get these. But the cool part about these equations is we take an energy balance, right? This is just an energy balance. The TdS, that's Q along a reversible path. du is like the delta U. PdV, that's work along a reversible path. So we take a thing where that typically has heat and work. Heat and work both care how you get from point A to point B. They're both path dependent. But we can kind of derive these equations, which are now no longer path dependent. So temperature, entropy, internal energy, pressure, volume, all of those quantities have defined values at a given point, and they don't care about what happened before or how you got to that point. They're just values. So we use these two equations to learn some things about entropy, and we got a bunch of different entropy equations. So I'm not going to rewrite all of them now. I'll just rewrite just one of them so that kind of you can at least remember what kind of equations we had. Okay, so we had so we derived equations like this was delta S equals the integral from T1 to T2 of CV over T dt plus R times the natural log of V2 over V1. Yikes. Okay, and another equation that we derived was delta S equals the integral. It looks almost the same, but it's Cp over T. This is minus R natural log of P2 over P1. I'll write a note in blue just because this is a kind of an important point. This is, again, we're kind of coming to a point where we have more equations, and the equations that we have more stipulations as to like when they work. So for these two equations, when do they work? These work for ideal gases. But they give us something, I don't know, there's something rather interesting about just looking at them and asking, what does it mean about entropy? Well, one thing, so we know a little bit about why entropy might go up, why entropy might go down. But if we look at these equations, we can see kind of the mechanics of how that works. So if we add heat into the system, that's going to be an increase in temperature. So if we're adding heat, that's going to make that part get bigger. So adding heat to a system, that's going to make entropy increase because that first part of that first term is getting bigger. Similarly, if we let our stuff take up more space, so the volume gets bigger, then entropy goes up because that term goes up. Or the flip side of that, right? If we add heat, this term gets bigger. If we let it get bigger volume, that would be lower pressure, which means that this term, if pressure goes down, that term gets more negative. We'll talk next week about some of the kind of more nitty-gritty details and implications of some of that, but we can start to see some of the workings of why entropy behaves how it does. But I guess I'll ask right at this point how, and we'll transition a little bit into new material now. So hopefully you've seen all of this stuff. If we have constant heat capacities, then we can simplify this a little bit easier because those first integrals, we can just solve them. And we get delta S equals, right, CV ln T2 over T1 plus R and delta S equals Cp. This is minus R natural log P 2 over P1. Okay. So those first two equations, those work with temperature-dependent heat capacities. We're not going to really do much with those. What we're going to do is do stuff with the simplified versions that work with constant heat capacities. Okay, and so what have we typically done when we've come across like something like a turbine and we've had to do something with entropy? Almost every time we said we have at least one time had to do, let's say, is this an ideal turbine? What does that mean? That means it's adiabatic and reversible. What does that mean about entropy? That means delta S equals 0. So what are we going to do with these equations? Same thing. What happens if delta S equals 0? What happens in delta S equals 0 processes? What we've done before is said, okay, that knowing that delta S equals 0, that tells us something about how we get from like an initial state to a final state. It tells us something about that process. And then we would use that information to then go and look up like the final temperature or final pressure or something like that in tables. We're going to do basically the same thing with this equation, except there will be no looking up. So let's look at what that looks like. So if delta S equals 0, yikes. Okay, so if delta S equals 0, then we're going to start with just one of those equations. Then we have 0 equals Cp. We'll look at the Cp version. We could do the same with either, but this one's a little bit, well, we'll kind of get everywhere that we need to with just one of them, so there's no reason to do both. So if we look at this equation, what we can see is that it is relating. Now it has two constants, heat capacity and R, Cp and R. But other than that, it has temperature on either side of the process, like at 1 and 2, and it has pressure at 1 and 2. So it's relating like an inlet and an outlet, or an initial state and a final state. And there are no, right, if we know everything about the initial state, and we know a single thing about the final state, that would be like, we know 3 of our 4 variables, we could solve this equation for the 4th variable, right? Just like when we looked up delta S equals 0, we said, okay, we know the inlet and we know the outlet pressure. Let's look up the entropy, and then that we can find the temperature that way. This kind of like saves us a step, but is doing functionally the same thing. So let's just solve it in a couple different ways that might be useful to us. So one way is maybe we know temperatures and pressures. Maybe we know pressures and volumes. Maybe we know temperatures and volumes, right? There are different ways that, the different properties that we might know. So we'll just solve it in a couple of ways that are going to be useful, or get it in a couple of forms that are going to be most useful. So if we have Cp, or sorry, natural log of T2 over T1, we'll just get these on opposite sides, equals R over Cp over the pressures. We can get the natural logs, we can get rid of those, equals, right now it's P2 over P1 raised to the R over Cp power. And now we have a handy dandy equation that relates the ratio of the 2 temperatures to the ratio of the 2 pressures. So if we knew, right, we could really easily solve this equation for a T2 equals. Just for the sake of some of the other stuff that we're going to do, we're going to do a little algebra up here. With R over Cp. So R over Cp, that right? R equals Cp minus Cv, the difference in the two heat capacities. So we really have Cp minus Cv over Cp. Again, this is going to feel a little bit weird, but we're going to do it, and then we'll figure out why we did it later. It'll make our lives a little bit easier later. If we multiply both sides by Cv over Cv, that equals Cp over Cv minus 1 over Cp over Cv. Right? We multiply by a fancy value of 1, and we get this. And let's just say that the ratio of the two heat capacities let K equal the ratio of the two heat capacities, Cp over Cv. Then we get, our previous equation becomes this. To the K minus 1 over K. Okay, and this is the equation that we're going to use most often. We can do, okay, so this is an equation relating temperatures and pressures. We could maybe think of a situation where we would want an equation similar to this, where we knew like temperatures and volume. How would we get from this equation to an equation relating temperature and volume? Well, we know the ideal gas law, right? So this is, this whole thing is only for ideal gases. So these are for things that the ideal gas law is what works, is what describes it. So use to get other pairs of properties besides temperature and pressure, right? So we have kind of three different things: temperature, pressure, and volume. We can get any pair of those that we want. So how would we with this? Well, we can say P equals RT over volume. And we could plug that in. So we would get, right, T2 over T1 equals R T2 over V2 divided by R T1 over V1, all to the K minus 1 over K. And I'm not going to do this because I don't know, I don't want to waste we don't have that much time left, and I want to make sure I get to other things. But you could imagine, you know, massaging some algebra into that equation and getting it to look a little nicer, so that we had, like we had before, like a T over T equals some function of volume. So we'll do that. This will be my symbol for doing that. Some algebra. And out pops T2 over T1. So the algebra gets a little bit ugly because you have weird powers and you have temperatures on both sides, but you can split it up so that temperature is just on one side and volume is just on the other side. You get T2 over T1 equals V1 over V2 to the K minus 1. Okay, if we wanted, again, another pair of equations, say pressure and volume.
That K minus 1 over K?
Nope,
Just K minus 1?
Just K minus 1.
Okay.
So the first one is K minus 1 over K. This one is K minus 1. And it changes in the magic of algebra. While you're trying to get the temperatures over on the temperatures on the right side, was you're trying to smush those over to the left side. That's when that drops out. So we can use the ideal gas law again, right? So PV equals RT. So we would get, say, P2 V2 over P1 V1, V1 over V2 to the K minus 1. So this one's a little easier to algebra. It's a verb, right? To algebra. So we're going to algebra this one, and right, how would we do that? Well, we could multiply both sides by V1 over V2. That would cancel the V2 over V1. It'd make it go to 1. So if we just take this and multiply by everything by V1 over V2, that would give us this new equation, P2 over P1, and this would add 1 to the exponent of the thing on the right, which would just mean that V1 over V2 to the K. All right, so we have these 3 different equations. They all do, I'm going to zoom out so we can see all of them. They all do the same thing. They all tell us something about systems where the process is a delta S equals 0 process. It tells us how what's coming in is related to what's going out, or how the initial state is related to the final state. It's related by these different equations. They're just massaged so that they're kind of in the variables that we want. Just to make it easier, we did some algebra with the ideal gas law. So the interesting one to take note of, or one interesting one to take note of, is this bottom one. So P2 over P1 equals V1 over V2, right? That would be how we, carry down our exponent. So we could split this one into, like, put the 1s on a single side and put the 2s on a single side. And if we did that, we would have P1 V1 to the K equals P2 V2 to the K. And this is kind of a weird equation, and it's kind of cool because it tells us that pressure times volume raised to the K power, K being the ratio of the heat constants, that the only way that that equation works is if both of those things are just constants, right? That P1 V1 to the K is a constant. It has a value. And P2 V2 to the K is a constant, and it also has the exact same value, right? That's the only way that that equation actually works. So this means that PV to the K is a constant in a delta S equals 0 process. And we're going to use that to do something kind of cool. So before we do, though, I would just say we knew something. We'll just do a really quick example. Again, there's a better example of this in this solving the Brayton cycle, of how to use these different equations to tell us about, okay, how do we get across the turbine? Well, we do a delta S equals 0. So then we use one of these equations. That goes through in more detail, but I want to do it at least briefly here. So if we have a process where right, P1 equals 100 kPa, P2 equals 600 kPa. And things happen. And out the other side is, sorry, not writing the wrong things. So this is P2 equals 600 kPa. T1 is 300 Kelvin. And things happen, but happen in a way that's adiabatic and reversible. So it's an adiabatic reversible process, a delta S equals 0 process. Right, we could solve for T2. Again, if we were doing this earlier in the class, how would we do it? We would look up the entropy of state 1, and then we would use that to look up temperature and or pressure and entropy and figure out what temperature that goes along with. We can just do it more directly here. So we can say that T2 equals T1 times P2 over P1. Well, let me just write it a little bit. Let's write it exactly how we have it before. To the K minus 1 over K. So if we know that K equals 1.400, so this is substance dependent.
And K will always be the same?
Nope, substance dependent, look it up.
Well, for a particular substance.
Nope, it will change with temperature, but these equations are based off of constant heat capacities. So for these equations to work, and again, what we're really interested in here is not getting all of the details exactly right. When you compare the Brayton cycle that we do in this example problem with the Brayton cycle that we did before, the numbers are not exactly the same, and that's because this is not exactly right. But the idea is to get a better physical connection as to how all of these things fit together. And this also gives you maybe a little bit better kind of rules of thumb for how different things affect each other and how how raising pressure and temperature, how those correlate with each other. So I guess the long answer is no. Things are more complicated than that. The short answer is for these equations to work, then we said that we'll pretend that it is for now. And again, we're doing that because we're not really interested with all of these methods in right answers, like getting exactly the right value for some design. Right? If you want to get the exact right value for a design, you have to go through and do more complicated models than this. But this gives you, we're interested in conceptual understanding for how some of these things work, if that makes sense. Because that's really, and I guess this is maybe I don't want to get too far on a tangent. But if you don't have an understanding of things at this level, then it's difficult to for more complicated processes and more complicated models, it's difficult to know what should I be doing, or what should I be thinking about changing or modeling even. Trying to connect a more complicated model. If you just dive into the more complicated stuff, you can really easily get lost and not know kind of what knobs to turn or what things to look at. Where if you can understand some of the more basic physical principles, then you can add in complexity and start to make it more true. But you have a foundation where you know how things work, if that makes sense, right? This is how we do engineering models. We start with simple mathematical stuff that's not actually true, but has some usefulness. And then you can add on layers of complexity to figure out exactly how things work. If you want to do projectile motion, you start with the projectile motion equations and you say, well, that doesn't take into account air friction. And it doesn't. but you can like add that in later. And if you don't understand just normal projectile motion, then you have no hope of understanding projectile motion with air friction and with, you know, the Coriolis effect and with other stuff on top of that, with wind and how does that. So you have to add in these things sequentially. And we're kind of at the point where we're looking at like, this is projectile motion for thermodynamics. I don't know, hopefully that makes sense. Or at least gives you maybe a sense of why we're doing some of this. Okay, so back to our example problem. All right, so if we wanted to know outlet temperature, well, now this becomes a really easy problem. It's not looking stuff up and interpolating. We don't have to plug anything into Cat3. We just plug in our values to this equation. And we could say, right, T2 equals T1, P2 over P1 to the K minus 1 over K. I'll just note these values for K, you can calculate them. They are the ratio of the heat capacities, but they're also, if you look in the table where we have heat capacities, there is also a column for K. So you don't even have to necessarily calculate K from the ratio of heat capacities. That's something you can just look up as well. If we plugged in numbers, we would get T2 equals, this is 300 Kelvin times 600 kPa over 100 kPa to the 1.4 minus 1 over 1.4. This would give us a final temperature T2 of 500.6 Kelvin. Put little like things of glory around it. An important point, I just used Kelvin. You have to use Kelvin. None of this stuff works. Entropy, all of the equations of entropy, just like the ideal gas law, all of these things only work with absolute temperature. So those all need absolute temperatures. Okay. But it becomes, with some of these equations, hopefully you get a sense of how we might use that. Again, this example, some of the examples that I do in the video, we'll do this a couple times, and hopefully you'll get the feel of it. Another thing that we might want to do, you get a new page. And this will be our last real set of equations, is we might want to calculate the work involved in a process like this, right? We already have an equation for work. So we could calculate work for a delta S equals 0 process. Right, that would be PDV. In order to calculate work, we need P as a function of V. So what we could do is, right, we could do this equals the integral. So this would be RT over V dV. And say, aha, now we turned pressure. It's not pressure now, it's a function of volume. And that is true, but now temperature is still here, and temperature is changing. So temperature is not constant. Again, if we look at the process that we just did, the temperature came in at 300, it came out at 500. So temperature is changing. So we would need something that relates both how temperature is changing and pressure is changing. We could substitute the ideal gas law in again, and we would be back in like the circular thing where we're just throwing ideal gas law at it. So we can't quite get there with just the ideal gas law. We have to be a little bit more creative. There are two different ways we could do it. One way that we could do it is we could do an energy balance. Right, we could use our energy balance. In this case, it would actually be fairly straightforward because this would be the Q12. If we know it's adiabatic and reversible, we know that equals 0, and we can cancel that out. So we could do that, and we could go through it, and we could say, okay, delta U, that's CV delta T. We know our two temperatures. We could calculate it relatively easily. We'll call this option 1. Completely valid, gives us the right answer. Option 2, and we'll see why for option 2, why we would even do a second option when we can do an energy balance. Option 2, we know P V to the K is a constant. And I apologize, we're going to go a few minutes over because I think we need to get through this equation. We know PV to the K is a constant. So we can write our equation, PdV. Right, we can multiply this by V to the K over V to the K and get was the integral of P V to the K over V to the K dV, and say, aha, the top part is just a constant. That's a constant. So W12 equals P V, not sub K, raised to the power of K times the integral of 1 over V to the K dV. And we can just integrate this. Again, this is going to be then equal to PV to the K times 1 over, right, negative K plus 1 times V to the minus K plus 1, evaluated from initial to final. Our general formula for integrating it with any value of K. Now, the cool thing is when we actually go through and do this, we get a simpler equation that this equals right, P. We have V to the minus K plus 1 and V to the K, both like multiplying by each other, so the K's will cancel out. So we just get P2 V2 minus P1 V1 all over 1 minus K. Okay. Yikes. Or we can use the ideal gas law and write that the work equals R T2 minus R T1 all over 1 minus K. So one of the kind of cool things that drops out of this is how work and really temperature are related to each other. Right? We've said kind of all along that we get more work out of a bigger temperature difference. We can see that, again, for an ideal gas, it's only related to the difference in temperatures. What's your high temperature? What's your low temperature going to be? There are also other similar equations. We can write a general equation, and we'll stop with this. With what we call a polytropic process. Where PV raised to an arbitrary power is constant. This is a polytropic process. They are real processes, like a real expansion, a real compression, that are not an ideal adiabatic reversible, but follow approximately polytropic processes where pressure and volume raised to some power where that's approximately constant. So this actually is a reasonable model for real things. It also works for a couple special cases. So if we have, right, the general equation for this then is, right, work, we would derive our equation the same way. P2 V2 minus P1 V1 over 1 minus N. So N equals K for a delta S equals 0. N equals 0 for a constant pressure. So N equals 0, so that's just P2 V2 minus P1 V1. That's an equation that we've already run into, which is really just a simplification of this more general result. There's also N equals infinity for a constant volume process, which would be one, right? The only way that we can get P times V to the N, if pressure is changing and volume is not, is to make N go to infinity so that it dominates and wins and the pressure change doesn't matter. So N equals infinity for a constant volume, and we have some number divided by infinity, so we get work equals 0. For a constant temperature process, that's N equals 1. That would just be PV equals RT. Then we have to go back and do our integral a little bit different because we would have like a 1 minus 1. So our equation doesn't work the same. So this is a special case. We could go back up and, right, we would go back up and do this integral, but now with, instead of K, we would do it with a 1 there. So we would do the same integral, we would just have a 1, and we'd have 1 over V. So instead of getting this, this kind of a general solution, we would get a natural log. So we would get that work equals PV natural log of the pressures. And we could use ideal gas law to get other forms of that. Instead of PV, we could substitute RT and we could change pressures for volumes. We could do some different substitutions of that. So that would be for an isothermal reversible process. So all of these, all of these equations work for reversible processes. And different reversible processes, we can use different equations to be able to calculate work directly. Okay, I feel like this is a lot of stuff to throw at you. I recognize that. And like I said, we're gonna go through and spend a good portion of the time next week. Hopefully you'll have some time to at least mess with these and try to work through them. We're going to spend a good portion of the time next week trying to put all of the different equations that we have together into kind of a consistent framework so that we know which equation goes with which thing. I think I'm going to do that in video form so that you can kind of do it on your own time. I may, I'm thinking about trying to make that video earlier rather than later and then just releasing it to you whenever I make it. So I was kind of thinking I may do that. I don't know if I'll get to it. I will not get to it today, but I might be able to get to that like tomorrow or Thursday and then release it to you later so you have that as you're going through this last homework assignment. If that's useful, and then we'd have a really light last week. But I don't want to like throw too much this last week, but we're thrown off a little bit with some of the scheduling changes and some of that whatnot. Okay. So again, I apologize. We're a few minutes over class today. Thank you all for hanging out and sticking with me. I'm going to end recording here, and then I'm going to hang around for